Hello everybody. Let's look at the homeworks from the second part of 10.2, especially bipartite graphs. So the first one was number 29. And that was about the marriage problem. And so we have a lot of blah blah blah. Let me not read all the blah blah blah. We kind of know what it is, right? We have boys that want to marry girls, and we somehow assume that they always consent. When when a boy likes a girl, it's kind of mutual always. Why? We don't really understand that, but okay, that's the given premise here. So we have Sandeep. So let's Sandeep here, and he. Let's get some. I don't know exactly how many there are, so we'll see whether I have too many notes or not. Sandeep wants to marry Tina. So here is Tina and Vandana. Okay. And then Barry is willing to marry Tina. Shah, and Uma. And then you see, I hope you appreciate it, just to make the graph from all the data is kind of a little bit time consuming, right? And one has to be careful there also. So that tells you that there's a lot of information in that kind of simple picture that we will have, that we call the graph. Okay, so go on. Teja, or Teja, I don't know exactly. I'm pronouncing this as if it's Spanish. So Teja is willing to marry Tina. Tina, we have already Tina. Okay, and Zelda. Teja wants to marry Zelda. And then Anil. Okay, Anil is willing to marry Vandana, and Anil is marrying and Zelda, and then Emilio, he is willing to marry Tina. So Tina is kind of popular, I guess, and Zelda. Okay, and I hope I didn't forget anybody. Okay, so the question again is there a perfect match possible? And using the marriage theory, disprove or prove that is possible. So, okay, how do you solve this? I already explained to you. The first thing one should do is to make what we call now the adjacency table or the neighborhood table. It's basically the same table, it's just a different name. So here come the boys, and here come the choices of the boys. So the neighbors, their choices, the girls that they pick. So Sandeep picks Tina and Vandana. Barry picks Tina, Shah, and Uma. Let me double check here that I'm taking the same information. Sandeep, Barry, Teja, Tina, and Teja. Okay, so we have a TE here. Tina and Zelda. Then Anil is willing to marry, if he's interested in marrying Vandana and Zelda. I'm just using the initials here, okay? Vandana, Zelda. And then Emilio is willing to marry Tina and Zelda, T and Z. Is that correct? Yeah, okay. So, what are we looking for? We suspect it's not possible. Now, it might be, right? But we don't know. So, let's suspect that it's not possible. Then we're looking for a subset of the boys. We know it has to be a subset, cannot be all of them, because there are 5 boys and 5 girls. Okay? And we want a subset of the boys. So, let's call that, like the book calls this V1, and this is V2, right? So, the boys and girls in this case. And so, a subset such that its neighbors is smaller in size than the subset itself. So this collection of boys there are more boys than they themselves select, the girls that they select. So we know already we should not look for just single guys because that's never going to happen, right? To make this has to be rather big to make this happen. If this is just one, this is never going to happen. If this is two, then you have to look for a set that has only one choice here, but that doesn't exist. So we see that every neighbor set has at least two elements. So this is at least two. So this has to be at least three in optimal case. So can we find, let's think about three. So let me write this up already. So is one is just not the case. Is there such a subset of size? Oh no, sorry, I write equals to one. I meant equal to one. So no, there's no subset like that. Can it be a subset of size 2? Well, no. Right? Because if this is subset of size 2, then this neighbor set should be only 1, but that doesn't. It's not possible. So no. The first possibility is 3, because the degrees. So let's list perhaps the degrees here as well. So the degrees is 2, 3, 2, 2, and 2. Okay, so any neighbor set has at least 2 sets, but most likely more because you're taking, remember, this is a union of such sets, right? So sigma has to be at least 3, and then we have to find a neighbor set of 2. So are there, in other words, what we're saying is, are there 3 boys that all choose the same 2 girls? No, that's not the case. So again, that is ruled out. You see, some things you can very quickly rule out just having the data, this table. And notice that I'm really looking, well, you don't see me look, but I'm actually really looking at the table rather than the graph. So the graph has all the information, but the table allows me to analyze it. Now, okay, you say that's a little bit silly, right? Because the question itself actually basically gave you the table and then you drew the graph. So you shouldn't have done the graph. True. But often you just get a graph and then you have to figure it out yourself. Okay, so next thing we look at 4. So now what we're looking for is this. Think about what we're looking for. We're looking for boys, these are the boys, such that they have only interest in 3 of the girls. All 4 are interested in 3 the same girls. Perhaps not all of them, but some of the 3. Is that the case? Okay. I think T and V and Z, T, V and Z, T, V, T, Z, T, V, Z, T, Z. Yes. So if let me color this, I'll do it a bit in orange, kind of. So if I take S, Teja, Anil, so S was Sandeep, right? And E is Emilio. Then as C, they all choose only 3 of the possible girls. So in other words, if sigma is the set S, T, E, Teja, Sandeep, Teja, Anil, and Emilio, then the neighbors of this set is the union, is all the guys that are listed here, and that is the girls are Tina, Vandana, and Zelda. So we have here that the set sigma is size 4, but the neighbor set has size 3, and this means no complete match. And basically in this case, if you want to analyze a little bit, is because Uma and Xia are not, nobody is really interested in Uma and Xia except for Barry. And so you, of course, you can see, I wanted you to do this, use the marriage theorem. Now you can argue much quicker. You can say, oh, look, Xia and Uma have only one suitor, Barry, and he has to can only take one. So either Xia or Uma will left without a viable partner. And so there already lies the problem. So you very often you can find quicker arguments like that, but if I ask you on a test or a quiz or so, I want you to use the marriage theorem. So I want you to show it this way. And notice that this is the point of view we take here from the boys. We look at what do the boys like. Where my argument saying that this is impossible is that because we reason from the side of the girls. We say Xia and Uma. Now we have to be careful a little bit because that's not enough to rule it out. Suppose, for instance, I'm going to make their graph different, so I'll make it in red. Suppose there's also Anna is here, and let's say Barry likes Anna, and Anil likes Anna, and and the right, yes, yes. And then perhaps let me take, I want to make sure what I want to do here is, yeah, okay, let's do this here. How does this change the dynamics? Well, let's see here. What is now added here is, so both Barry and Teja now like Anna. Now my previous analysis falls apart because in my group that I have here, the four guys that I was looking at, and they're only interested in these three girls, that's no longer true, because Anna all of a sudden showed up, and I always said, oh, Teja said, oh, Anna. And so this means that this count is no longer correct now. The neighbor set of this set in the new the line includes Anna here, which has now size 4. Okay. Now, why I'm saying this is because now the argument about Shia and Uma doesn't work anymore. You can say, oh, right, Shia, Uma, one of them will, only Barry is interested in them, so Barry can only pick one of them. So one of them is going to left out. Yes, that's okay, because there are 1, 2, 3, 4, 5, 6, and only 5 boys. One will be left out, no matter who. No matter how we do it, there's always somebody that's going to be drawing the short straw here. So that's why I'm saying, sometimes you can analyze it from a perspective, but it is kind of what we call, I don't know whether you understand exactly what this means, it's ad hoc. So, and, oh, let me write it up. It's Greek, it's Latin, ad hoc. And it means an argument is ad hoc, means you came up with the argument on this very specific situation, but if you have a similar situation, your argument might not work anymore. And this is what mathematicians do not like at all. Mathematicians like something that, a procedure that works always, an algorithm. Ad hoc is almost the opposite of an algorithm. And marriage theorem is an algorithm. It says, calculate all the neighbor sets of all possible subsets, which is a lot, by the way. There are a lot of subsets. If you remember this from your counting, if you have, here in this case, we have 5 guys. How many subsets of size 5 are there? 2 to the 5th. 32 subsets. So it's kind of a lot of calculation. Now, some of them we know we can rule out. We can rule out the subsets of one element. We can also rule out the whole set. So that's already 5, 6. Also the empty set, 7. There's still 25 sets to check if you want to do this like automatically. In other words, if you want to put this as a computer, an algorithm. We can reason quicker, of course. So, but the marriage theorem is an algorithm way of solving this. Reasoning by what I did with Shia and Uma is ad hoc, and as I said, just by adding one certain element, it's no longer valid. And in fact, I kind of suspect that we can now make a complete pairing here. Let's see. Let's see whether with this new thing I can do a complete pairing. I think if I make oh, I said that Teja likes. I'm sorry. It's not Teja that likes Anna. Oh, sorry. Let me try to. Oh, my eraser is too thick. That's why. Okay. So sorry, I put it in the wrong spot. Right? It doesn't make a difference. It's Anil that likes Anna. Okay. But it's still. So this is no longer true either anymore. Now, so this is no longer true, as I said. So we cannot reason in this with this subset anymore. And I think there might be a matching. Let me try. I'm gonna match Anil with Anna. Where is Anil and Anna? Okay. Oh, this red line is confusing me. Sorry. Okay, no. Okay, so this was not part of the graph. So this is now part of the graph. So this is one matching. Then if I do, I have to be smart here. So I'm gonna Sandeep with Tina. So okay, so let's do. We have already Anna is gone, and now Tina is gone. So that tells me, and I have already done Sandeep and Anil. So what is left? Oh, from looking at what Teja here, we can only match him with Zelda. So okay, so you go there. So that takes Teja and Zelda. Zelda is out of the picture. Oh! I made a mistake. I think there's a solution, but I think I took the wrong solution. Okay, I'll leave it up to you to check it out. Okay. I want to do the other question because I don't want to make this too long a video. That was so. Sorry, I stopped perhaps a little bit too brusquely, but what I'm saying is, look, I now have scratched out everything for Emilio, so he has no choice anymore. So I didn't choose this properly. I think Sandeep should not have taken Tina, he should have taken Vandana. Tina is very popular, so the most popular one we should keep as long as possible. She always has a lot of choices, so I think that was my mistake. Well, okay, I'm kind of now curious myself, so I'm gonna kind of try to. I'm gonna give it one more try. Okay. So okay, I have to put in this extra N between Anna and Anil, and let me make this all black, otherwise I get confused. So now I have to get rid of these eliminations that I thought were necessary. They're not correct anymore. Okay. Okay, I'll try again. Actually, let me take care of Barry, because Barry has to take either Shia or Uma. Otherwise, if I don't take either one, then I'm gonna have too few girls. So Barry is gone and Shia is gone, and Uma is also gone somehow because nobody else is gonna choose her. Okay, so now it all comes down to choosing this correctly. Oh, sorry, this I forgot to erase this one. We have not done this right. Yeah, okay. Okay, so this means Anil has to take Anna, because otherwise nobody else is interested in Anna anymore. So Anil has to take Anna. That was correct. So Anna is gone, and Anil is also gone. So now I have TV, TZ, VZ, and TZ. TV, TZ. No, what I'm saying. Everybody likes T, so that's okay. Oh, but only one of them. No, that's okay. So Sandeep has to choose. I'm going to make Sandeep choose Vandana. So V is gone. As I said, originally I paired Sandeep with Tina, which is she's so popular that I should have waited with that. I should have chosen less popular. I'm not saying that it always works, but I'm saying common sense says that might work better. Okay, so Deep is gone, so is then Vandana. So now I see I have no choice. No, everything. Oh, okay. I still can do whatever I want. Tejana can go with Tina. Okay, now I'm gonna end. So Tejana with Tina, and then Emilio with Zelda. Okay, so we have a perfect matching from the point of view of the boys. So every boy is matched with one of his preferences. But so the matching problem is always in one direction, actually, right? So here it is from top to bottom. But suppose if we want to match, you can ask the same question: is there a perfect matching with the girls to the boys? So from V2 to V1, and the answer is no, because there are 6 girls and there are only 5 boys. So actually here, so if we now want to match in this direction, so it's now is there a matching from girls to boys, which is not the same problem, at least not when there are different numbers, and the answer is no, because if I take the whole set V2, its size is 6, but what is the neighbor set of this set? Well, by definition, it has to be V1, and that has only size 5, which is too small. So, okay. So now the last one, the other problem was number 43. Okay, there we have so possible degree sequences 3, 3, 3, 3, 2. It's a fancy word of just saying, okay, you have 5 nodes, 5 vertices, and these are the degrees of these that you want it to be. Let's put the 2 guy here and 3 here. Is it possible to draw a graph with these properties? So what you try to rule out is if there is, so remember, one condition has to be met: the number of odd degree vertices has to be even. Now here there are 4 of those odd ones, so these are the odd ones. That's an even number. So in other words, this is not contradicted. That is hopeful, but see, that's not necessarily means that it is possible. Okay, so 3 here. Now we have to start coming up with ideas here. Now, for one thing, let's look at the smallest guy here. So we can take the biggest one or the smallest guy. I sometimes I cannot tell you what's the best strategy here, but I feel like there's only one guy with degree 2, so let's take care of them. And actually, he has to, whichever this the grade 2 guy is, he has to pair with two of the three, with two of these guys, which all have degree 3. In other words, that doesn't matter here, right? So I can take these two, but I can also take the other two. It's the degrees that we are talking about. We can rearrange them. If I had chosen these two, the two links to this and this guy, well, move them around, put these guys here and put these guys there, and you have the same picture again. So, okay, so that takes care of the two guys. So now all the other have to have 3 between them. Okay, so I cannot. This guy can no longer link to 2. So he has to link to the 3 other guys because he has to get degree 3. And the same for this guy. He has to link there. He has to link there. Oh, this graph. I'm just trying to do what I need to do, and here's the graph. It satisfies exactly what I want to do. Okay, so B. In B, the degree sequence, or let me just draw it. I'm not going to do it as the questions I said is the same, but I like to draw things. The graphs are about drawing, so why not do that? So we have 1 with degree 5, 1 with degree 4, 1 with degree 3, 1 with degree 2, and 1 with degree 1. That's what they're proposing. Sorry, 43 number. Yeah, because sometimes I read the wrong question, and that's why sometimes things get really bad, right? I did this once in a video where I used the wrong initial conditions. I wrote it in a comment in the book, in the video. Okay, so what about this one? The answer is no. Why? Because let's count the odd ones. Odd, odd, odd. 3 odds. 3 odd. That's not allowed. So, okay. So no. Okay. C is the sequence. Look, sorry. Let me put something here because I keep looking at the wrong thing. 4, 4, 3, 2, 1. 4, 4, 3, 2, and 1. Okay. What about the odd ones? 1 odd, 2 odd. So 2 odds. So that's okay. That checks out. But just because it checks out doesn't mean that it's possible. Let's see. Perhaps it is, perhaps it's not. If it's possible, we have to be able to find one. If it's not possible, well, then you have to argue that it's not possible. Okay, here's my argument. Let's look now we could start with this guy, but I'm actually more interested in these two guys. Why? They are of degree 4, and let's think about the first one. He has to connect to 4 other vertices. There are only 1 left. So he has to connect to everybody. So 1, 2, 3, 4. It has to be that way. He has to degree 4. The only possibilities are those 4. Now, let's reason with this guy. Same reason. He has to connect with everybody. He's now already connected to this guy, so he has to connect to that. He has to connect to this, and he has to connect to that. Oh, whoa, 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 whoa. This is already something that we want. We have now 2. Because we have 2 guys of degree 4, the degree 4 guys in a set of 5 have to connect to everybody else, which is not possible if this one guy has to only connect to one single guy. So there's no possible graph of this configuration, which is, as I said, it does satisfy the theorem. So it doesn't violate the theorem. That's not the reason why it doesn't happen. It doesn't happen for a different reason. Okay, D is the sequence 4, 4, 3, 3, 3. So I'm going to here write the sequence again, because here we see 3 odd. So again, the answer is no. And then the last one is no, there are 3, 2, 2, 1. Well, okay, 3, 2, 1. No, 3, 2, 2, 2, 1, 0. So okay, let's count the odd ones. Then we can rule them out. If there are too many, no, there are 2 odd ones, so 2 odd. So okay, that checks out, but doesn't mean that it exists. So now we have to figure out whether we can make one or not. So here are things. So this is going to be 3. I'm going to make these guys 2, this 1, and let's make this 0. The 0 guy is easy. Can I do the 0 guy? I did it. Right, because there's no edges, right? I did it. Okay. So, oh, but that also takes then care of the 3 guy. The 3 guy can only connect, he has to connect to 3, and there's only 3 left. He cannot connect to the 0 guy, so he has to connect there, he has to connect there, and then connect there. So that's the only thing I can do. Now this also takes care. Let's put green for those that we take care of. So we taken care of this one. Well, taken care of this one. Now we took care of this one. But look, we also took care of this guy, because he can only have 1. Luckily, we see the solution here. We put this 2 here, and so we see here that such a graph does exist. Okay, so we have. That's the first time we have a graph that existed. No. A was also a graph that existed. Okay, so, and then let's do F. That's the sequence again is 1, 1, 1. All 1 guys, no, because 5 odd. That is an odd number of odds. That's not allowed. Okay, that's easy, right? So just for the heck of it, the 2 that I have, are they bipartite graphs? Why not ask that? You could ask it about any simple graph. Is it bipartite or not? So let's quickly go through it. There was not part of the problem, but just that you see how these things work. Because there were other problems where you had to do this, but I didn't assign them as special problems. I hope you do. I hope that you're not just doing the special problems, right? Do all the problems I assign. There's a reason I assign all these problems. The special problems are just problems that I think you might have a little bit harder time with, so I'll solve them for you, that you have hopefully no more questions. And by the way, if you have questions on something, please email to me or let me know in some way that we can address this, right? Okay, so is this bipartite? Remember, you color 1, and once you have made a choice, you pick 1 random, but then you're stuck with all the neighbors have now to have the opposite color, which is in this case pink or red. I don't know exactly. It looks like red, but it comes out as pink. Okay. So let's see. Okay, so we took care of this one. That's now taken care of. Now the red guy. No. Notice that this is in violation here. We have 2 red guys connecting to each other, so not bipartite. Okay. What about my other pretty boy here, number from E? Sorry, it's gonna be difficult to get rid of. Just make this smaller again. Just the color. I have to get rid of the colors, right? Okay. Okay. So let's color things. Well, I'll do red now, I guess. Now, okay, I can color the 0, but does it matter what I color 0? No. In a bipartite graph, the ones of degree, the isolated vertices never going to play a role, right? They can be in either side, actually. That's what it means. But let's look here. So I'll make this red. But by making this red, all the others have to be green, because they are connected to it. And again, so I start one with a high degree because it makes a lot of colors appear. And I can already see that there's a clash here again. So we have a clash here. These 2 should not be connected. So again, the answer is no. Not a bipartite graph. By the way, let me draw another graph here just to give some example here. Is this a bipartite graph? Let's look at this. Just a simpler graph, right? Is this bipartite? So again, I color this red. But once I color this red, I have no choice. These 2 have to be green. So, and notice that all these 3 are okay. There's nothing else I need to do anymore, so they're all fixed. So what about this guy now? Well, that's the thing. We have a choice. We can make it red or green. So if this is a bipartite graph, if this is A, B, C, and this is D, I can put the graph this way with these guys on top, and A goes to B and A goes to C, or I can make it this way. Both are the same bipartite graph, but kind of visually put different. And well, sorry, they're the same graph, but not the same bipartite graph, because these are the V1 here, where this V1 is only 1 single guy. Okay. Talking about complete matching. Which of the 2 cases does have a complete match? Not the first case, right? Because I cannot match D with anybody because he cannot be matched. He's like, he doesn't want to marry anybody. He wants to be a celibate. Okay, so In the first case, I cannot match everybody. In the second case, sorry. So so this one is there's no complete matching. But here is a very simple one, right? I pick whoever A wants, and that's it. That's a complete matching. Remember, complete from V1 to V2. Remember, a complete matching from matching from V1 to V2. We should always kind of make it clear what the direction is, but very often that's understood. It is from the V1, the top ones, if you draw it this way, to the bottom ones. Okay, so in the second scenario, yes, there's a complete matching, because complete matching means that everybody of the V1s is matched. And that is the case. Everybody in the V1s is matched. Not everybody in the V2s, that's true, but that's just obvious because there are 3 of them and there's only one guy on top, so it will never be. Okay, just that was not part of the question, but just giving a little bit more background on these problems that you might help you with the other homework problems.